This is our last presentation. It's an investigation into future rainfall extremes within North Carolina for state transportation needs. The presenter is Dr. Jared Bowden. He's a senior research scholar at North Carolina State University in Raleigh, North Carolina. His expertise is the application of numerical weather and regional climate models, and has developed downscale climate change projections using regional climate models for the contiguous United States, US Caribbean, and Africa. His research has been used to inform many downstream climate change applications, including ecology, air quality, and hydrology. His work has been used to help inform several US global change research programs, reports including the 4th National Climate Assessment and the impacts of climate change on human health. Part of his ongoing research emphasizes characterizing uncertainty in changing precipitation regimes for air quality, ecological, and hydrological applications. Dr. Bowden is currently participating in the 5th National Climate Assessment.
So first, thanks for sticking around. I know if you're as hungry as I am, I would probably just walk out. but yeah, so I'm actually a climate scientist and started working, actually came in 2017 and gave a talk about climate change and the implications for design. And actually Roger back then was thinking about how to update the intensity, duration, frequency curves. And I think he's done an excellent job, and I really appreciate what the community's trying to do and what I say is it's like you got to kick the ball and get the momentum, and I think that's happening now. But even then, I think there's still a lot of challenges in thinking about climate change. I have to give a lot of credit here to my colleagues at NC State, especially Professor Gary Lackman, and his student, Katie Hollinger, which did some of the simulations that I'll discuss here. So starting with this is simply saying, there's a recent paper that came out, I think it's in 2019, but looking at the hydraulic design standards and the frequency of rainfall events, there's basically a signal there, and we should be concerned. And simple physics of the atmosphere basically tells you why we should be concerned, because as you increase temperature, as global temperatures continue to increase, the saturation vapor pressure of the atmosphere increases. But basically what that means is if you have enough moisture available, then you can rain it out. And that's our big concern. And so I think we should all have to think about what that means. And if you think about it with respect to temperature, it's not a linear increase. It's actually exponential. So the saturation, vapor pressure, and temperature relationship is exponential. And we're at this low end right now. And actually the global climate scientists all agree that once we get above 2 degrees C, which could be as early as mid-century, we have really big problems on our hands that we have to start thinking about now, today, because 30 years from now, if we continue along the current emission pathways, there's a lot to be concerned about. So I think it's really critical to think about working with climate scientists. I know it's hard. Everybody says I'm already burdened, I have a lot to do, and that's completely understandable. But I think in the future, we need to really start talking to each other more, and that's kind of why I'm here, is just that as a climate scientist, I want to be working with the engineers to help you think about how to best use climate data for your applications. And so in this study here that I'll talk about, I'm focused on a unique comparison of updating IDF curves for the state. And I'll say why it's unique in a few minutes. And then there's also another aspect. There's a lot of this 2D rain on grid modeling that's happening. And climate scientists actually have experiments that might be very helpful in applying to these 2D grid models, these rain-on-grid models for future applications. And I'll talk about that because I'll be talking about future hurricanes, and I'll be showing you simulations of future hurricanes here in a few minutes, and the rainfall that comes from those storms as the climate warms. So when you look at this, we should consider how to best apply the climate models, but at the same time, we take the best available data, but we also have to, at the same time, think about, well, what are their limitations? And so I put here, you start with the global climate models, and these global climate models are fairly coarse and aren't really able to provide you really good information about daily rainfall extremes, for instance. But there are methods such as downscaling methods, and that's what, if you go to the CMIP tool that Roger and them have created, they use the statistically downscaled climate change projections to then inform their IDF curves. But there's also limitations in those available data, not just the global climate models, but also the downscale projections. And there's a really important limitation for the state of North Carolina, and that these data sets really don't say anything about hurricanes, and hurricanes are driving a large portion of the large floods for the state in recent years. So there's a huge limitation in thinking about just using that data itself. So as I said, the GCMs don't really represent these, and that's why we have these downscaling data sets. So the most popular method of downscaling the global climate models to provide precipitation for your applications is statistical downscaling. In the National Climate Assessment, the fourth National Climate Assessment, that's what was used to make general conclusions about how rainfall extremes are changing in the climate now and into the future. And there's basically very different data sets available. One is called LOCA, which the CMIP tool that Roger's provided you guys is using. There's also other data sets, which is called MACA, and MACA is a different statistical downscaling approach to provide daily precipitation into the future. And the grid length of these data sets are less than 10 kilometers, so they're fairly reasonable. But the thing about it is that when you look at it, there are assumptions behind these data sets. And stationarity assumption is a possibility of being a problem because you're training using historical observations, and you use that trained relationship to then look at what the future may hold from the GCM and in the future. So a more physical modeling approach, and this is what I do, and I've been doing this for almost 2 decades now, is called dynamical downscaling. And basically, you take everybody's seen the weather forecast and how, let's say you're going to forecast what the tropical storm may look like or a hurricane may be coming, and you see it. These are limited area numerical weather prediction models that do these things. You can actually apply these same models, but under a future climate, and that's what I do in my study here, is I'll be looking at some of these types of experiments. So the big question is, we have all these different data sets and methods. Do you get a similar result at the end? That improves our confidence. We want to improve our confidence in how climate change is going to impact our extreme weather and precipitation. And so I'm going to be comparing the different methods. I'll be comparing the statistically downscaled data sets, that LOCA and MACA data sets that I just talked about, against dynamical downscaled data sets that I'll discuss in a few minutes. And then I'm going to address one of the significant limitations of method 1 and 2, which are the statistical and dynamical, through some idealized climate change experiments looking at hurricanes. So I don't want your eyes to kind of get blurred out here, but why is this comparison unique? Basically, there's these different methods, which we said the statistical methods, which are, let's see if I can figure out this pointer. Up here, these are the statistical methods, and these are all the different GCMs that are downscaled using those methods. The dynamical methods are very expensive and computationally take a really long time to run. And so you'll find that they're hit and miss. There's not as many of these. And these are different climate models, regional climate models, that downscale these global climate models on the right. But just to say, you can make some intelligent comparisons here if you overlap the same apples to apples, the GCMs you're downscaling. And that's what I'm going to be looking at in just a second. So there's a simple way, and so Roger provided some 10-step methodology to doing this, but basically it's a fairly straightforward process, and making the IDF curves is this: once you have the daily precipitation, you create your annual maximum series, you fit a distribution to it. Here we're going to be doing GEV, generalized extreme value, and then you have the IDF curves, and basically you find the cumulative distribution, and so you can find that 0.99 event. And then you develop a scale factor, so you'll do that for the historical and future climate, and why you do it and you do relative differences is just that these data sets don't properly represent the intensity of precipitation that's observed. And so we already know there's a limitation in the data set itself. And so we do this scale factor ratio analysis because they're biased. And then we'll apply that scale factor ratio to our observed rainfall depths. What we're doing with the North Carolina Department of Transportation is slightly different than what Roger and them are doing with the CMIP tool. And in our case, what we decided to do is that, as mentioned earlier, rainfall is a stochastic process. You can get one value saying one thing and the next grid cell saying something very different. And you need to think about that's noise, and you have to smooth out that noise. And one method to smooth out that noise is to look at different ways of aggregating. In this case, we're going to aggregate the data over different climate divisions. And we're going to be looking at a mid-century and end-century period for these different return periods from 2 years all the way up to 100 years. So this is an example of basically the precipitation depth in the historical climate, which is in blue, and then that pinker shade is towards the end of century. And this is basically the ratio, but this is the distribution for one of those regions. And so you'll see that you get a large range of values, and doing point by point for a single GCM can give you a lot of noise. And so if you want to do a cross comparison between GCMs, it's best to try to think about how do you filter that out. And in this case, we basically find the median scale factor between the historical climate of all of those points in that distribution and the future climate. And that's what we use as our scale factor here. It's basically a climate division scale factor, not for a single GCM. And so we applied these scale factors to the median value of the IDF values for a given county that it falls in. So if your county falls within that climate division, you know you can go to NOAA, you can find the centroid of your county, get your IDF values, and then apply that scale ratio to then look at the future. And so here we're looking at in-century of range of rainfall depths between 17 of the same GCMs that were downscaled. So that box plot is the range of GCMs for different axes or the different methods. And so we have LOCA and MACA. These are the two statistical downscaled data sets going from 10 years all the way to 100 years. And on the right in green is 100 years. Somehow or another it got cut off on this screen here, but basically this blue is the 10-year, these horizontal lines are the 10-year, for instance, the 25, the 50, the 100-year. And then these are the like 500 and 1,000-year observed values that you would pull out of NOAA Atlas 14. And so what is this really saying is that here's the 10-year, right, and here's the 25-year. This is the future values. And so you can see this blue, which is the 10-year, has now flipped to like a 25-year storm. So basically you're scaling things up. You almost like it's like a scaling things up all the way around. The same thing, so the pink and this yellow line is the 50-year observed value. This is the range of GCM answers that you get when you take that method and you look at it and you apply it to rainfall. And basically now you're basically thinking about scaling it up again. The same thing with this one. So your 50-year, which is the yellow, becomes like into green. And what gives you a lot of confidence is that majority of the GCMs a lot of times fall above that range, which is a sign that, hey, we need to think about doing something. And this is one way that we're doing this. We're doing this for every county. And so every county within North Carolina will then have rainfall values like this for different greenhouse gas emission scenarios, different statistical downscale data sets, as well as the dynamical downscale data sets. But one thing that really comes out of this is that these methods are right beside each other. LOCA, MACA, two different data sets you could make a decision off of, gives you different answers. And basically, always we find that MACA is larger than LOCA. And LOCA is what we're currently applying within the CMIP tool that we're thinking about using. And then that makes a question, are we using the right scale factor? This is uncertainty. It's a different method, different data set, gives you a slightly different answer. And so I wanted to investigate that question by then let's take a look at the dynamical data sets and make that comparison. Even though there's fewer of them, will it give us basically a sign as to, is LOCA right or MACA right? So that's what I was just saying. And so here is the scale factor. So this is just a scale factor. So I have one to, actually it goes up to 3. And some of these in the MACA data set, and these are the different GCMs downscaled colored. So you can see there's only 4 of them, but there's 9 in that very far right is the dynamical, which is called Cordex. But these are the dynamical simulations. These are the physical models that we run at higher resolution to resolve those things and not try to think about it in a statistical framework. And basically what happens is that you'll find that LOCA looks more like Cordex in the dynamical. So it gives us this sense of confidence that LOCA's probably on the right path, and MACA, if you were to apply this data set, and you can see the range gets really large and funky in MACA between the different GCMs. And so the big takeaway is I think we're on the right track of using LOCA in this for our analysis. So this is just the preliminary results, but I think for the IDF curves, but just the big thing is when you're thinking about generating IDF curves, understand that different data sets can give you different answers. And so there's going to be CMIP 6. This is CMIP 5. CMIP 6 is coming out now. The National Climate Assessment is currently working with CMIP 6 data. It's out there. It's available. At some point, we might be thinking about updating with the latest and greatest science. And so will this hold tried and true? Will we see the same thing? It's yet to be seen, but I think that's something we have to keep in the back of our minds as we move forward. But the big thing that take-home message here is that in all instances, there's a very simple approach to IDF. Can you just think about scaling up? So 10-year becomes a 25, same thing, the 25 becomes 100. Is that something simple philosophy that can be applied or not? And I'm not a designer or engineer, so I can't really answer that. So the major limitation in all of these data sets that we talked about before is North Carolina has been impacted by major hurricanes. And you think about Florence, Matthew, Floyd, dating back all the way to 1999, has created significant flooding in eastern North Carolina, creating billions of dollars in damage. So how can we overcome the limitation of this? And basically, you can then take these limited area weather models and simulate that hurricane, whatever hurricane of interest you have or storm of interest, in the historical climate. And then you can think about, well, how would that same storm look like in a warmer climate? So take, for instance, what drives hurricanes' energy a lot of times? It's the sea surface temperatures. If the sea surface temperatures increase by 4 degrees Fahrenheit, what's the impact of that on the storm? And you can generate experiments like that within this environment. And then basically you'll have a simulated historical storm, a simulated future storm with rainfall that's actually output hourly or even finer. So you can get at looking at sub-daily things in a better means using these type of methods. So I'm going to give you an example of Hurricane Matthew, and I'm really hoping that this talk kind of bounces off the next generation of people thinking about how to think about climate change, what these experiments actually can bring to your DOT. So this is Hurricane Matthew. I'll talk about it. It happened in 2016, extreme rainfall event. You're looking at rainfall totals during the storm upwards of 19 inches, and it created almost around $10 billion in damages. So these are the atmospheric models, and I don't expect you to understand what I'm talking about, but here we use what's called the Weather Research and Forecasting Model. It's one of the weather models that are actually used to forecast the weather today, tomorrow, next week. But you can apply it in a sense in this framework. So we go down here to a 4-kilometer grid over the southeastern US to look at these hurricanes. So the first thing to look at is that, do we do a good job at simulating the rainfall from that historical hurricane when you compare it to observations? And the answer is, if you look at both the track and the rainfall in general, yes, we do a pretty good job. We're able to simulate the precipitation associated with that storm. Is it perfect? No. But at the same time, it is giving you some really good rainfall rates and rainfall totals when you make this comparison. But let's take a look at towards the end of century under a very high greenhouse gas emission scenario. So think about the worst of the worst, almost like that. They don't really like us to say worst case scenario in climate science, by the way, but I like to say it anyway because it makes sense to me. So here's the historical simulation, and here's the end of century simulation. And if you look at the rainfall totals, the maximum rainfall totals increase greater than 50%. This is larger than what we're typically seeing when we're scaling using LOCA or IDF curves. So, but it's a process we're also missing within that data set. So it's almost like telling us that, hey, we need to think, if you're thinking about hurricanes as important for your area, then you might be on the higher end of those local values when you think about design if you want to think about hurricanes. So one thing is like, if you're wanting to do some 2D rain on grid modeling, you want the rainfall maximums to kind of align. And unfortunately, with these methods, sometimes the storm track itself will shift in a warmer climate. But you can relocate the maximum precipitation within that model domain and kind of shift it to where the observations are. And so we did this here, and just a simple comparison, you can see that, you know, it does a pretty good job of putting where it was previously in the historical simulation up in here over southeastern North Carolina. So what about the hourly rainfall rates? And so this is the rainfall rates of 1.5, 2 inches, 2.5 inches in an hour. And how will that change in a warmer climate? And it's very obvious that the rainfall rates not only increase, but the spatial extent of where those heaviest rainfall also increases. So the storm footprint increases when you think about rainfall. And so that's another thing to think about, is it's like these storms, when we're scaling them in this environment, like using IDF curves and scaling them, we know that storms aren't going to be homogeneous, right? They're not going to give you the same thing everywhere. And it's very obvious that in this case, the footprint of the storm increases as well as the intensity. So this is just looking at the number of hours with rainfall rates during the duration of the storm greater than, for instance, 2 inches increases at a 178% increase. That's a lot. There's a lot of heavy rainfall that falls with this storm in a warmer climate. So the summary is that right now, if you're looking at these storms, that you can expect maybe 50% increases in total precipitation or even larger, and that the rainfall intensity and frequency of coverage increases more than 100%. And we have simulated other hurricanes, Floyd and Florence, and the preliminary results indicate it may even be larger in some instances. And so we've seen, for instance, in Florence, which stalled over eastern North Carolina, has greater than 75% increase in total precipitation during the duration of the storm. And I want to end with this because you probably don't have an appreciation of what I mean when I say I'm simulating these storms. This is the actual loop of water vapor in a historical climate and in a future climate for this storm here. And so this is Hurricane Floyd. And so you can start to see in the historical climate, the water vapor, the atmosphere is not as moist, right? It just doesn't have it. In that future climate, that storm gets way more moisture available to it. That's why it dumps so much more precipitation out. So these are actual simulations. And so you can think in a rain on grid sense, you'll have hourly precipitation or finer that you can then provide to your 2D rain on grid models to maybe help you think about those limitations and how do you actually think about resilient design, because not everybody has the same problems. And climate models aren't, they might be good for one application in one region for one problem and maybe not for another. In this case, hurricanes is a real serious issue for eastern North Carolina and the broader southeast. And these type of simulations, I think, help us get at looking at this. People have looked at doing these type of simulations for Hurricane Sandy, Hurricane Harvey. Climate science community is doing this, and so I'm just putting it out there. It's a resource that others may also find useful for their applications when they're thinking about resilient design. So I thank you, and hope you guys enjoy lunch. Yes.
Yeah, great presentation. Thanks for sharing. So this simulation is showing the changes to the actual precipitation from the same type of events. Do you have any thoughts on the frequency of future events occurring and maybe landfall? Like, will there be also more hurricanes, not just stronger hurricanes?
So the science right now doesn't say that there's an uptick in the frequency. If you look at simulations, there's basically thought that the frequency, at least for the North Atlantic, it's not projected to increase, but it's more about the intensity of these storms. Yes?
Are you familiar with the Canada tool for IDF changes under climate change?
I've seen that, yes.
How come there is a tool for Canada, but there's not a tool for the US?
Good question. Yeah, so there's a question is Canada has a tool for creating IDF curves for the entire country, and what are we doing? It's been a very regional approach within this. Besides federal highways going out and doing what they've done so far, there's been, the Northeast has done it, Chesapeake Bay has looked at it. I've seen some Florida studies that have done some things, but it's been very regional. And I think engineers don't want to get stuck in having to, do all of the work. And so that's why we're trying to create the IDF curves for the state with the best science we have. And the best science we have right now is those statistical downscale data sets like LOCA, which Cordex, which is a dynamical, kind of puts it on the same footprint. But so yeah, so to answer your question, it's been very regional for the U.S.
Have we heard of Atlas 15? What is going to do?
What's that?
Atlas 15?
I can't really speak about Atlas 15. Yeah, I don't know if Atlas 15, Matt, maybe you know if they're going to think about future. I think NOAA, and I don't know for sure, has kind of stayed out of the climate change arena with IDF curves to some degree. So they haven't really done as much. I think they like to look at their observational record and updating that. So Matt, I know that they're going to be doing some pooled study to update the IDF curves, but to my knowledge, I don't think they're doing anything about the future climate. Yeah, the Mid-Atlantic, the Marissa tool, those are those regional approaches, but thinking about like for the U.S. as a whole, yeah.
I think that's good.
Yeah.
Thank you very much.
Yes.